Hi, in this video we're going to focus on this second equation of the ELO algorithm, the one that updates the player's rating. We see you have the original rating, the k-factor, the actual score or outcome versus the expected probability, and we get a new rating. So now we'll similarly go back over to the Desmos calculator and look at some equations. So we have up top, these equations aren't visualized, but I just put them here for reference. This is kind of what I just showed in the other video. If we take this portion and just represent it as, what's changing, we see the changes, the k-factor times the difference, and the difference is the expected versus the actual outcome. So on the right we have this graph here, which is, as you can see, this kind of linear function here. You can think of this as sort of a bias term or an offset. And this is, think like a slope or something. And we have at the max, we know that this probability is in the range of 0 to 1. It's probably never going to equal 1 or never going to equal 0 because of the asymptotes of the other graph. Or never actually approaches 1 but doesn't equal 1, and it approaches 0 but won't equal 0, stuff like that. But then the actual score that a person achieves is constrained to 0 for a loss, 0.5 for a draw if your game uses that, and 1 for a win. So you can see here how at maximum someone can gain K points, and at minimum they can lose K points based on the sign of this difference. So if someone is highly expected to win with 95% chance of winning and they win, the difference is actually going to be close to 0, which means this multiplication is close to 0, which means they don't actually get many points. You see this green line is very close to 0. So where it intercepts, they would only get 1.6 points. So it's k times 0.05. But if they lose, if they see the players lose but they were expected to win, we now have a difference of minus 0.95. And this times k, you can see at this point here, is they would lose 30 points in their rating. And you can see I talked about in the article how the difference between the expected versus the actual is what really controls this here. And this visual gives you an idea of how you can play around with possibly different things. So let's look at the other equation real quick. What's probably obvious. If the person was expected to lose and they lost similarly, there's almost no change. They would lose a similar 1.6 points. But if they end up winning, then the difference jumps all over to the positive sign, and the person would gain 30 points or so. And if they adjust this parameter, we can, I think in the article I called it the sensitivity, and the kind of rationale is here is if the k is too low, when a person wins they don't gain that much, and so even if a person gets better at the game they're playing, their rating won't go up as necessary, and they'll have to just keep winning and it'll be annoying. If the so it's not sensitive enough. If it's too sensitive, let's say it's really big. If I get lucky and win one game, my rating jumps up really high, and I can possibly gain 40 points and be facing people who are way above my actual skill level. And then I'll just lose, and that might be frustrating, and it might be contribute to instability in the algorithm. So I think over time people have realized that the base of or scale of 400 and the 32 factor here is nice, but these terms are kind of arbitrary based on the parameters your game has and what you want humans to feel the numbers as, of in the range of thousands, or if you wanted to, technically you could get rid of all this and keep it in the range of 0 to 1. But yeah, I hope that better explains the rating update algorithm. Thanks.